Welcome everybody. Today we will talk about the hydrogen production plant, one of the most important units in the modern refinery nowadays, which feed this hydrogen pure to hydrodesulfurization unit, hydrocracking unit. Main units in the refinery use the hydrogen and process the hydrogen to implement some category of processes like cracking processes, treating processes. We will go deep through this knowledge in this lecture, and we will know the general concept of the operation of hydrogen production plant, especially the reformer. We will discuss the process design and the main parameter and the mechanical design also, and some control loops will be discussed in detail, but I will focus during this lecture on the reformer. What is the hydrogen production plant and what is the reformer? Here, the gas generation by steam reforming is applied for the production of hydrogen, carbon monoxide, synthesis gas, reducing gas, may be used in ammonia plant, may be used in methanol production, or any other petrochemical type of hydrocarbons. When we discuss this diagram, it's clear that the first stage of the hydrogen production plant is desulfurization for the natural gas feed or feed gas to the unit. And this happens by two reactors, R1 and R2 here. The first one, which is COMOX catalyst reactor. This reactor with some additional hydrogen, like 3% from the total flow, will react with the sulfur components and switch all these sulfur components into H2S, which will be removed by the second reactor here, R02. We use the ZnO, the zinc oxide, in the second reactor. The zinc oxide converted into ZnS and leave the gas clear from any sulfur component to go to the main reformer. And I need to discuss the reformer here in detail and add some new knowledge related to the reformer. A hydrogen reformer is not a single reactor, but reforming processes unit, complete unit, whose main reactor is tubular catalytic reactor, fired from the top. The main function is to convert the hydrocarbon, mainly natural gas or lighter component hydrocarbon, with the steam into hydrogen-rich gas or synthesis gas. Okay. Here, the main objective from this reactor is to produce hydrogen. The conversion reach here around 75%. Okay, to produce hydrogen for hydrotreating, for hydrocracking, for ammonia plant, methanol, as we mentioned before. Reduce the methane content, generate synthesis gas. Synthesis gas, this word related to hydrogen, CO, CO2. This is a synthesis gas, okay? The reactor type, fixed bed tubular reactor can be used, tube bagged with the nickel-based catalyst, tube installed inside a furnace, operate like a plug flow reactor. So what we need to mention here in this step, this is the reformer. The reformer inlet temperature around 550 degrees C and outlet between 800 degrees C and 900. This is tubular, can be considered a special type from the plug flow reactor. The reaction happened here in this reformer is endothermic reaction, okay, and the main reaction happened here at this condition is CH4 plus H2O, okay, will give you CO plus 3H2O. This reaction is endothermic. You add heat and the reaction consumes this heat. The inlet temperature at this point is 550 degrees C and the outlet is around 850 degrees C, okay? This reaction occurs inside the reformer tube. This reaction occurs here inside the reformer tube. The rate increase with increasing the temperature and limited to the equilibrium. Is there any other reaction happens? Yes. For example, if there is a C2, what will happen? C2H6 plus H2O, the steam, will give you 2CO plus H2 hydrogen. And the outlet stream here is too hot, so we need to apply the heat recovery principle by producing steam using the boiler feed water, okay? And the outlet temperature is around 350 degrees C. This stream continue, we need to increase the conversion. We go to the shift converter here. The shift converter will increase the methane slip, okay? And convert all the CO2 in the presence of H2O into more hydrogen and CO2, okay? And the methanation reaction is CO plus H2O will give you more hydrogen and more hydrogen and the CO2, okay? So this is the shift converter main reaction. CO plus H2O will give you CO2 plus hydrogen. Then we will remove this CO2 and other component using the BSA at the end of the unit. So the main reactor here is the reformer, and we will see the shape of the reformer in detail. Heat recovery and shift converter, high temperature shift converter. This catalyst is 3 type of catalyst, FeO, which is iron oxide, Fe3O4, and chromium oxide, and some copper oxides to stabilize and promote the reaction at lower concentration from H2O, okay? So this stream heat recovery also, and then cooled and separated by hot separator, then cooled and the cold separator, then you go to the BSA to complete the purification by the pressure swing adsorption to produce your final pure hydrogen. This is the roughly general idea of hydrogen production plant. I want to focus more on the reformer in this lecture. I want to give you many shapes or diagrams related to the reformer. Let's see together. Here the reaction which is CH4 plus H2O in the presence of temperature between 800 degrees C to 900 degrees C will give you CO and 3 hydrogen. This is endothermic. Some side reactions, which is exothermic, like CO plus H2O will give you CO2 plus hydrogen. The overall is endothermic, okay? This is what I want to tell you here in this lecture, which is we used to find that reformer to produce hydrogen is up-fired, okay? Up-fired design. But I want to clear to you that there is many other design, like side-fired reformer here, okay? And this is the shape in the side. And this terraced wall reformer, which is angled, the angle type burner will be used to give the reaction temperature to the reactants, and rarely you will find this bottom fired reformer, okay? So the cost considered to choose which one from these shapes to choose this advantage for top fired for sure, for the stability, complexity, for the maintainability. This is items you make comparison and the cost control for sure, okay? And side fired and the terraced wall type, okay? This the different type related to the reformer as a mechanical design. So we learned at this moment that the overall process flow, you have to make treating for the gas feed section here, the feed section, sulfur removal, and the mixing with steam here, with the steam ratio are from 2.5 to 3. This is high pressure steam for sure, because the reaction between CH4 and H2O, okay? And reformer furnace, which is tubular, and we saw in the diagram, it can be up-fired, side-fired, or terraced, something like that. And then you have to apply the heat recovery and produce steam, then the shift converter and cool the stream, then the BSA to make what? To remove the residual CO2 from the stream and give you hydrogen with purity around 99.9. Okay, we have here some tips like the temperature, for example. The inlet temperature of the reformer, as we mentioned, 550 degrees C and outlet temperature around or between 800 to 900 degrees C. Okay, what is the furnace flame temperature? Near 1000. Okay, the pressure. The pressure for this reaction is typically between 20 to 30 bar. A higher pressure reduce methane conversion but require for the downstream unit for sure. Okay, what is the steam to carbon ratio here? Between 2.5 to 3.5. The minimum is 2. You should not go lower than 2 as a steam to carbon ratio, and I think there is a 3 point related to this ratio. Okay, high steam to carbon ratio prevent carbon cooking on the catalyst tube and improve the catalyst life and increasing the operating cost. Okay, this is the high steam. When you increase the steam to carbon ratio, you improve the operating parameters related to the unit, but one side effect is increasing the operating cost. Okay, what is the space velocity related to this type of reactors? It is between 1000 to 3000 hour minus. As we know, the liquid hour space velocity unit is hour minus. Okay, low space velocity, high conversion. Low space velocity in this reformer equal to high conversion. What is the catalyst inside this reformer? Nickel based catalyst supported on alumina, high sensitive to sulfur, so we make this desulfurization or hydrogenator and desulfurizer. Okay, and the highly sensitive to sulfur chloride and ability to make coke formation on the catalyst. Okay, so the catalyst here, nickel based catalyst supported on alumina and high sensitive to sulfur component and chloride, and you can say it's sensitive to halide in general. Okay, so what you will do if you remarked a little cooking and increase in the delta B on the tube related to this reformer, what you will do, the symptoms to this criteria is rapid pressure drop increase across the tube. This is one. Loss in methane conversion. Okay, and hotspot can be found also. Hotspot can be found here. And the catalyst deactivation and the possible tube plugging. Okay, all this related to the reformer. How you will deal to correct this this criteria and what to do to discuss the root cause. First, let's discuss the root cause. Okay, low steam to carbon ratio can lead to this carbon deposition. Okay, here on the tube, the low steam to carbon ratio can lead to this criteria: low operating temperature and the high carbon content C2 plus, which is heavier, and sulfur slip killing the active nickel sites. Okay, you have to remark this. And poor feed mixing between steam and the natural gas at the steam mix point. The corrective action to protect the catalyst inside this tube is to increase the steam carbon ratio immediately and increase the inlet temperature, reduce the feed rate, and check the sulfur guard bed performance at R1, R2, and avoid rapid load change. Okay, to work right. What you will do if you remark hotspot or overheating along this tube? The root cause can be flame impingement or distribution for the firing system inside the reformer, or the catalyst channeling itself, or coke laydown, or burner misalignment. Why the coke laydown can lead to hotspot? Because the reaction here in the tube absorb this temperature. So if you remark that the temperature starts to appear at the surface of the metal, this means that there is no good reaction inside the tube to absorb this temperature and will lead to hotspot. So the corrective action to handle this hotspot is to adjust the burner flame, balance the fuel gas distribution, and inspect the catalyst loading near shutdown, and reduce the firing rate in some cases. And if it go excessively, you have to shut down to solve the problem related to hotspot. Low hydrogen production from this tube, like low hydrogen purity, high methane slip at the outlet, or the BSA reduction in the recovery. What if the root cause can be low reformer temperature lead to this, catalyst aging lead to this, and high pressure, low residence time, poor shift conversion in R03. Okay, and the corrective action related to this criteria is to increase the furnace firing, to reduce the feed rate, to check the catalyst aging and activity, and verify the shift converter by send sample to the lab, adjust the pressure if possible. You can do something like that. Okay, so this is the gradient related to the tube behavior. Okay, at the outlet the temperature start to increase because the rate of reaction here is high, and start to decrease when we go through the reaction near to the outlet along the tube. Okay, and here is the distribution of the burner and the tube, and mechanically you can consider like what I'm telling to you as a general concept. Okay, the spacing row to row, the spacing row to row is 2 meter point 1, 2 meter point 3, and the spacing wall to row, the spacing wall to row, okay, this can be 1 meter point 6 to 1.8. This is a generally concept. Okay, I want to emphasize on this. Spacing tube to tube is 260 millimeter to 300 millimeter, and the tube inside diameter, which is very important because of the delta B along the tube, is very important also, maybe 4 inch to 4.5, and the ratio tube spacing 1.8 to 2 millimeter, and this is the general mechanical concept related to the tube arrangement and the burner arrangement. Here is a photo from the site itself, clearing the the burner itself distribution, and between each row of burner you will find the distribution of the tube. Okay, this is the reformer side view, and this is the inlet section. As you see, this is the radiant section, and this is the outlet section, which collect the hydrogen product by the big tail. This big tail sent this gas to the header to apply the energy balance and producing the steam from the exchanger downstream the reformer. Okay, so tube rupture is important consideration related to the reformer. This shape give you the place of the big tail, as we said, and the collection header, and the cold outlet preparing to produce steam by the attached to steam disengaging drum, and this is the refractory here inside this part. Okay, this is the inlet from top to bottom for sure. Okay, and this is considered as the inlet subheader, as you see, and this is the outlet. Tube rupture we can discuss now. What is the symptom for the tube rupture? Sudden pressure drop. Okay, furnace flame instability, high O2 or CO in the furnace, and emergency shutdown immediately. Okay, the root cause can be what for this criteria, which is tube rupture or tube leaking. Okay, can be long-term overheating, because the heat distribution using this huge number of burner is very critical. Okay, and metal creep or carbon attack, poor metallurgy. Okay, is this a poor metallurgy through this metal tube? It will be very, very critical and can lead to tube rupture. The corrective action is immediate emergency shutdown, nitrogen purge, tube inspection, and review the flux design. High pressure drop across the reactor. I mentioned that the delta B across this tube is very, very critical. What is the symptoms for this high pressure? Increased in the compressor load if you are working with a compressor to supply the feed, reduce the feed throughput for sure, and uneven equal temperature. The root cause can be carbon formation for this criteria, or catalyst fins, which make resistance to the stream or the flow or the fluid going through the tube deformation, or salty deposition on inside the tube itself. Okay, the corrective action is to reduce the load. You have to reduce the load and increase the steam ratio for sure. Plan to make decocking or catalyst replacement. Check the feed contaminants. Here we mentioned that there is a many arranged burner to give you the required heat of the reaction. If you remarked flame instability, the symptoms can be like flame lift off, okay, or flame impingement, a high CO in the flue gas outlet. You have analyzer at the bridge wall outlet, okay. So the root cause to this criteria is the fuel gas composition change or the burner fouling itself, okay. Or you have to check the air for board distribution through the burner itself, okay. And the damper malfunction, you have to check. Corrective action is to adjust the air to fuel ratio, clean the burner, or readjust the burner on, the burner off, which is critical. Okay, some cases it's implemented by vendors here, burner off, burner on, related to the capacity. Balanced draft control and verify at the stack the O2 concentration to solve this problem, which is flame instability. Okay. What you will do if you remark a poor temperature profile along the tube. The symptom is very clear: cold inlet, hot outlet, imbalance, localized hot zones through the tubes, reduce the conversion. The root cause can be maldistribution of the feed for sure, and the channeling in the catalyst bed, and the inlet distributor maybe damaged. Okay. The corrective action is to inspect feed distribution, reload the catalyst properly. I want to tell you that after we make loading for the catalyst through the H tube, we make measure for the delta B by special device, not to face problem like this in future. For each tube here, when you install the catalyst, you measure the delta B to be away from this problem. Use correct catalyst grading. Okay. This is general idea related to the hydrogen reformer as a reactor. This is one of the rarely reactor working with endothermic condition in our industry, because normally you find the reactor work with exothermic reaction. Here you are working with endothermic reaction, okay, and this is the main consideration. And finally, for this lecture, not to make the time too much, I want to tell you that this tube should be free to expand, and we ensure something like that by this suspension system. For the reformer, you will find suspension system to ensure that the tube is working flexible. Okay. Here is the illustration and the construction activity for the reformer. And finally, I want to show you the shape of the burner top fired. And through our lecture, we know that there's a many type of the mechanical design of the reformer, as I mentioned it to you here. One of them is top fired, which is the famous measure of the hydrogen production plant working with top fired. Okay, and there is a benefits from this design. As I told it to you, the maintainability is low, the distribution for the catalyst tube is optimum, and something like that. Okay. And if you are working with narrow area and low cost or something like that, you can select side fired. Okay, side fired, because the burner here is installed in the side of the wall, and this terraced wall with elevated angle burner, and rarely to find bottom fired reformer. I hope that I could add some new knowledge or information to you through this lecture. And finally, as we used to say, appreciate it and thank you. Okay, thank you so much.